Hi, thank you so much for that introduction. Space of mobile, of development, and I'm going to be convincing you that deep learning is the perfect solution for a whole host of problems in outer space, and this is the perfect time to be working on that. So, we send thousands of sensors into space every year on spacecraft. These are multi-million-dollar spacecrafts. These are CubeSats, which can fit into the palm of your hand. And the sensors range from they range from internal sensors that measure what's going on in this spacecraft itself. So they measure the temperature in the spacecraft, how the spacecraft is working. They're sensors which face outwards, like the Hubble telescope. It looks at outer space, it looks at stars, it looks at what they do. They're sensors which face Earth, that measure what's going on the surface, that try and analyze all of that. But these things don't work perfectly. In fact, those Mars landers, it takes 7 minutes to go from the top of the atmosphere to the surface. 7 minutes. The time it takes for a signal, a radio wave, a communication signal to go from Earth to Mars is 14 minutes. That means during the most critical point of this spacecraft's mission, it has no way of getting back to Earth, getting information back to Earth. Not only is there no way of getting stuff back to Earth, but Earth has no way of controlling it. And this has led to a crash of a very famous ESA rover called I'm going to butcher this name, Schiaparelli. Right? What happened was there was a problem in the GNC system. It was a control problem, and it crashed midway through. It didn't deploy the chute when it was supposed to. Earth didn't find out about this until the rover had crashed on the planet's surface and was unable to do anything else. But it's not only the control, it's also the analysis of this data that we get from space. How many times has the weather been wrong? Right? I didn't come here with a rain. We have more serious consequences. We use this data to detect objects, detect things for disaster relief, right? And we mess up more often than you think. Clearly something has to be done. Existing systems don't work. Is deep learning a solution? Yeah, it seems to be. It's working. It's a state of the art for everything we're doing on Earth. For most of these vision-based tasks on Earth, it's the state of the art. Control, robotics, we see stuff coming into self-driving cars from deep learning every day. Satellites are complex systems. They're systems which have lots and lots of data. There are systems where we've had data from these systems since 1960, when TAROS-1 was the first meteorological satellite that actually gave us data that we analyzed for the weather. But just imagine what we could do if you used all of this data, all of these things, and applied deep learning to them. This. For those of you, this is an evil AI from the movie 2001: A Space Odyssey. So we can make evil AIs in space. But despite all of that, deep learning is the way forward. And the reason right now is the perfect time to actually look at that is because the systems that facilitate deep learning, which are absent in space, are now making their way into actual spacecraft. Why? You can use deep learning in a plethora, in everything. You can use it while these spacecraft are going up. You can use it while they're in space, while they're landing, while they're docking. You can use it for the data they generate. Every single aspect of a spacecraft's lifespan has potential to be improved with these systems. I'm going to focus on two. I'm going to give some examples and applications of systems where deep learning has already been applied. I'm going to look at payload systems. So those are systems where the sensors are focusing outwards, the purpose of this mission. And I'm going to look at the operation of a spacecraft. So those are where the sensors are facing inwards. They look at maybe how the spacecraft is navigating, how it communicates, what are the power systems. Right? So we've seen payload data all over the place. Right? We've seen it when it does weather prediction. We've seen it when it tracks whales and penguins. We look at it when you get images of vegetation. Every time there's a part of the rainforest goes down, what you see on your news feed is payload data. It is hyperspectral data. But hyperspectral sensors aren't all that there are in space. There are other sensors as well. You use SAR sensors, LiDAR sensors. You have sensors for low Earth orbit or medium Earth orbit missions, which look at the atmosphere, that look at currents in the atmosphere, and that look at what are they called? For very low Earth orbit, sometimes even humidity, and you can also, there are all the systems that we look at with the payload data. These systems process that data on Earth. The data is, we get this data in space and we go to a base station, we do the processing, and we get some output from that. And we get great output. They're deep learning systems. So quite recently, we discovered exoplanets. That's planets outside the solar system with this data, with some of these telescopes. The James Webb Space Telescope and the Kepler Space Telescope, both of these use DNN-based systems to look at, to discover brand new artifacts, which happen to be planets, galaxy clusters, even asteroids that are coming towards Earth. But all of these things are on the ground. It's because compute is expensive in space. And as satellites are getting smaller, you get CubeSats, nanosats, these restrictions on this compute, which I'll cover in a bit, become even more stringent. Right? What about operations? If you're going to be operating stuff, if you're going to be doing guidance and control on a spacecraft, the guidance and control has to be, the algorithms have to be running on the spacecraft. Right? However, we've just started the sort of machine learning and the sort of deep learning approaches that we have just started coming into this realm. Most of them are still in Earth. It's like a pre-alpha 0 stage for this, for all these algorithms. You have communication algorithms, right? You have most of the, previously you used to have multiple antenna, that looked at multiple frequency or multiple bands. Now they're being replaced with software-defined radio. And software-defined radio, the protocols for these sort of things, they're techniques which use reinforcement learning, which show tremendous increases in efficiency on Earth. Navigation and control, right? You got in Surrey with the development labs that go through, that show considerably better system automation, that show considerably more robust and more resilient navigation capabilities. You have docking, you have DL systems which are used for docking and positioning of spacecraft. Right? Previously, things that used to be hard-coded with sort of signal and system sort of processing things are now being made adaptive. You use things like Foster. There are approaches which are being tested on Earth which use things like Foster CNNs. There are approaches which use YOLO for natural feature tracking on asteroids, and similar things. But the issue is we don't have operational data. Deep learning is one thing. It requires lots of data. We don't have these data sets yet, right? Hopefully, going forward, maybe this talk will spark it. We'll get some more data sets. We'll be able to do stuff here on Earth, rather than the simulations that we do, rather than the sort of test bed cases that we've made in very specific instances. But the true benefit of this deep learning will be when we can bring it onboard spacecraft, right? And for that, we need the platforms. We need these platforms to support the sort of computation that deep learning requires. But why is it so difficult? What's stopping us? One, volume, power. It takes $10,000 to send 1 pound into space. Power. These things have a very tight power envelope. They've got solar cells which have about 70% efficiency in the best case. And they power everything. They power every single system. And there are smaller systems which are battery powered. They have to be even more careful about how they spend that power. But these look very similar, right? This is what mobile computing, embedded computing, these are constraints we see there all the time. My cell phone has stuff like that. So why can't we just adapt algorithms from them? No, while there are algorithms which look at quantization, energy-efficient approaches, these algorithms aren't, there are other factors in space which make it far more difficult. Space systems require very rigorous verification. Space is a very harsh thing, which is a very harsh environment, which has radiation, which makes these systems, which makes these systems fail quite often. They have errors there that are both single point errors and cumulative errors. I'll be going more into detail about the radiation right now, and I'll talk about verification as one of the future opportunities for work in this area. Yeah, so how do we handle this radiation? Making a system robust to this is called radiation hardening. And there are physical approaches where you actually change the materials that are being used. There are circuit-based approaches where you add circuits that can correct for this sort of thing. There are approaches which integrate both software and hardware. In fact, the newest supercomputer in the space station by HPE uses software-based radiation hardening. But it has a downside. It makes these systems almost twice as slow, and it makes these systems very, very expensive, right? Hardware that's been radiation hardened has caught up. Historically, we had ASICs. Now we get smaller satellites, more players. As we have more players, smaller satellites, we've got almost Earth-like hardware that's been radiation hardened coming into space. We've got multiple processors, we've got FGPAs, we've even got some GPU-like accelerators that are going into space. But software is also there. Software and hardware need to do this thing hand in hand. And it's happening. Rather than the very specific, almost thin layer of software that we had, we have systems which are going all the way up to Linux, which are being deployed on satellites. But what exactly, how much, what is the benefit that I can get? I'm saying deep learning is great, but what is this benefit? In a small case study, I'm going to show that I can give you almost twice the power benefit by using a deep learning model. So we talked about space and weather. A lot of the images that come from space are of clouds, right? This is not very useful for most of our use cases. In fact, 66% of the Earth, on average, is covered by clouds. If I were simply able to identify these images and compress them, I'd save a lot of power. So we did a hypothetical, this is a hypothetical case study where we looked at an imager which had 512 by 512 pixels, 3 bands, and it processed this stuff on a Leon 3 processor, which is radiation hardened. And we used MobileNet V2 with the 8-bit quantization, right? And 300 MADs. And this particular setup, on the Leon 3 processor, it gives us 20-to-1 compression using this particular model. And that compression includes taking out 66% of these images. Transmitting that gave us a 2x power saving. The amount of data was reduced so significantly that the power we saved, primarily in transmission, was double, right? And after that, the opportunities are everywhere. You've got new applications. I told you the hyperspectral data is very different from the RGB stuff you see on Earth, right? You've got multimodal, multi-satellite approaches. You've got all this hardware just going into space. Can you distribute compute to make it more resilient? Can you distribute it to make it more powerful? You can do health for astronauts. Mental health for astronauts is very important. And one of the largest things, we now have a branch of the military. The US now has a branch of the military which is dedicated to space. Imagine if you had a deep learning guided missile in space. Huge applications, both for and against. Right? With all these things, you need to develop new approaches to look at this compute, to actually use it. Approaches which look at memory, power, reliability, that are aware of the context, of the errors that are happening, that are able to look at shared systems which are previously not there. And finally, verification. The verification things, the standards are woefully inadequate, and we need to rethink of the entire thing. I can go into this in a bit more detail if you'd like, but I think I'm running a bit short of time. Finally, I'm going to conclude by saying space systems Our space systems are they're a brand new area of mobile embedded systems. They're very distinct from the ones we've encountered so far. There's new hardware coming into space with software to support it and algorithms and algorithmic ideas that we can adapt for space. And it's the right time to be here. But there is likely to be a lot of opportunity, a lot of difficulty in getting new ideas adopted. And that's another one of the problems that we might have to deal with as this stuff goes ahead. Thank you.